Welcome to Physics Can Be Fun with me, Stephen Thomas. As you can see today, we've got electric circuit problems, and this is from 2018's final November paper. Let's have a look at it. Question 8. The battery in the circuit diagram below has an EMF of 12 volts, there we see it, and an internal resistance of 0.5 ohms. There we see the internal resistance. Resistor R down there has an unknown resistance, and then they're going to ask us, the very first question is, what is meant by the EMF of the battery being 12 volts? So, the first concepts that we've got to know are EMF and internal resistance if we want to successfully solve this problem. So let's see if we can go to an actual live circuit and just show you what is meant by EMF. So there I've got a voltmeter. Here I've got a battery. Now these are 1.5 volt batteries. The EMF of this battery should be 1.5 volts. Let's just see what it is actually. So here we've got a negative, there we've got the positive. And you see that it says 1.44 volts. That would be the EMF. There's no current flowing, and that is the maximum voltage that this particular battery can put out because it's a fairly old battery. Now imagine that I took this piece of copper wire. As you can see, it's a thick piece of copper wire. Let's again get... And what if I just take that piece of copper wire, let's see if we can show you here, and I just short it out. Do you see what happens to the voltage? Went from 1.44 to 0 volts. Every time I push this against the battery, it's going to 0 volts. That's because I'm doing something that is called a short circuit. So let's go back to here. What I'm trying to show you is that a battery has a voltage anywhere between its maximum voltage, which is its EMF, and naught. If you short it out, the voltage will drop to almost 0. If you have a normal light bulb, it may drop from 1.44 to, let's just say, 1.2 volts. So the first concept we've got to understand is EMF, and the second concept is internal resistance. Now, EMF has the Greek letter epsilon. It looks like a backward 3, a very curvy 3. You could say a retarded 3, epsilon. So EMF, it's on our BFF. Let's go to our best physics friend. So let's go to all the formulae that are involved with electricity. So there we see some of them. And there you see EMF, or epsilon, equals I, that's current, R, external resistance, R, internal resistance. So what is internal resistance? Maybe you've never heard of it because they don't tend to deal with it, obviously, until you get to Matric. You know what an external resistance in a circuit is, but did you know that there's actually a resistance inside the battery? The electrons actually struggle to get through the battery, then they go to the external resistance, and then they come and they struggle again to get through the internal resistance of the battery. And so that we can think of it as there being a tiny little external resistance here, and then we get our main circuit resistance. So we could take this internal resistance, put it outside for all practical purposes, and just treat it as in series with the rest of the external circuit. So internal resistance is the resistance that is sitting inside the battery or cell. Here's Ohm's law written with resistance equals volts upon amps. We must also know that volts is amps times resistance. Here's resistors in series. Here's resistors in parallel. We've got our EMF formula. We've got charge is amps times time. And then a few work and power formulae. So let's go back to the first question that they're going to ask us. Do you see how this here represents this whole battery, the square battery? And they've just taken the actual resistance of the electrons getting through the battery and they put it here, and it comes to half an ohm. It's not much, but it is significant. And then 12 volts is what this battery reads when there's no current flowing, and it's the maximum voltage. So the first question they're going to ask is, what is the meaning of the following statement? The EMF of the battery is 12 volts. So let's go to the memo. Now they give a whole host of definitions of what EMF is. The battery supplies 12 joules per coulomb. I don't like that definition. The potential difference of the battery in an open circuit is 12 volts. I kind of like that. The battery does 12 joules of work per coulomb of charge. Maximum work done by the battery. I don't like the maximum energy supplied. The battery supplies 12 joules of energy per coulomb. Don't like any of those. The greatest potential difference that can be generated by a battery is 12 volts. I like that. So I'm going to just learn one of those definitions, or two of them at the most, and then I'm going to quote them. Learn the definitions from past papers. Okay, so that would be your EMF. In practice, what it is it's the maximum voltage when no current is flowing, or the maximum potential difference, same thing, voltage, when no current is flowing. So that's when your battery is not under stress. We've seen that when the battery is under stress and it's short circuit, for example, its voltage can drop from 12 all the way down to 0. So what is the reading? Let's just move this a little to here. The reading on the ammeter is 12 amps when switch S is open. Calculate the reading on the voltmeter and the resistance of resistor R. So that's 3 and 2. So what are we told? We're told that that is 2 amps when the switch is open, and then calculate the reading on the voltmeter and calculate the resistance of resistor R. So the reading on the voltmeter, do you see that this is a closed circuit? There is current flowing, so that is no longer the EMF of 12 volts. Some voltage is going to be dropped here, and voltage always drops across resistors. That's in series with that. We can ignore for the moment this part of the circuit, because you see there's a switch there, so no electricity is flowing through this part of the circuit, so we can effectively ignore it. And here we have voltage drop there, voltage drop there. But before the voltage even gets out of the cell or battery, it has dropped a little bit due to that resistance there, and then the voltmeter will read it. So it'll be slightly less than 12 volts. What will it be? Well, if you look here, this is the positive side of the battery. That's the negative. The voltage at the negative side of the battery is always 0 volts. And the voltage climbs across the battery, and at this side, which is the positive side of the battery, it's going to end up as being 12 volts, the maximum, which is 12 volts. So in the battery, it goes from the negative terminal 0 volts, and it goes across the battery and it becomes 12 volts. Then as it exits the battery, as the electrons exit, they're going to drop a small voltage here. So now the question they're going to ask is, what does this voltmeter read? So let's put a question mark there. Okay, what is that voltmeter going to read? So it's going to be slightly less than 12, and how do we work it out? Well, I say they're the same thing you do for every single circuit problem, and this is actually a reasonably easy problem. We're going to look for something in the circuit that has got two of Ohm's law's properties: volts, amps, resistance. Which of these things do we know? So what do we know about this resistor R? Do we know anything about it? We don't know its resistance. We know that 2 amps flows through it, so we know one of Ohm's law's thingies. let's go to that voltmeter. We don't know anything about that. We've got to work that out. So let's go to this resistor here. You see the current is going to flow. If we take conventional current flows from positive, it's going to flow through that one, flow through the ammeter, flow through there. So it is the same current that flows through all of these, through that resistor and that resistor. So what do we know about this resistance? We know two things about it. They give us the ohms and they give us the current flowing through it. So now we know current and resistance. We know two parts of Ohm's law. Therefore, we can easily work out how much the voltage drops across this. And remember, resistors in series are voltage dividers. This 12 volts will be divided between that and that. So resistors in series are 12 volt dividers. So let's go to our Ohm's law again. So we go to our memo, to our BFF, or best physics friend. There's Ohm's law. We want to find voltage. So voltage is equal to I times R. So volts equals IR. What is the voltage drop? And voltage is always dropped across resistors, is I times R. Which I? The I they give us. Which R? That R, which is the resistance of that resistor. So I times R is 2 times a half, and so that's going to be 1 volt is going to be dropped across there. And therefore I now know that 11 volts is going to be dropped across here. 1 volt is going to be dropped, I times R. I can do it by mental arithmetic. And if we go to the memo, we'll see that they do the same thing. So let's go to that. They say here, volts equals IR. There's I they give us, there's R they give us. 1 volt is the drop. And but they asked us for the reading on the voltmeter. So now it was 12, it drops by 1 volt. So now we are left with 11 volts between there, and the 11 volts is going to be dropped across the only other resistance. This ammeter has no resistance, so it must be 11 volts. But how do I work it out? Well, I'm going to say EMF minus this voltage dropped by resistor R is 12 minus 1, and therefore the voltage that comes out, which is called external potential difference, they used to call it terminal potential difference, but I see this exam calls it external potential difference, is going to be the EMF minus the voltage dropped by the internal resistance, 12 minus 1, so that voltmeter is going to read 11 volts. Let's have a look at the memo. So here they say EMF minus the lost volts, the voltage that is lost by the internal resistance is also called lost volts, is 12 minus 1, 11 volts, and there's our answer. And then they give us a few other options, which frankly that's easy enough. So memorize it. Let's go back to the question. And the second thing that we asked is the resistance of resistor R. Now, have a look at this, that if you look at this, there's a conductor to here and there's a conductor to here. Do you see that all of this, there's no resistor? The voltage that is across this voltmeter, which we now know is 11 volts. Okay, so that's 11 volts. It's going to be 11 volts there. Well, it's going to be actually 0 volts here, but 11 volts there, 11, 11, 11, 11, 11, and then back to 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, all the way back to here. And there it'll lose another one, and then we're back to our 12 volts, 12, 12, 12. But as it came out, it's actually already in this dashed area, which is the battery. As it comes out, it's already lost 1 volt. So it's going to be 11, 11, 11, 11, 11, 0, then it drops the rest of the way and goes 0, 0, 0, all the way back to there where it's 0. So we now know the voltage across this resistor is going to be how much? 11 volts. So there's the 11 volts. So we now know two things about this resistor. We know the voltage across it is 11 volts, and the current through it is 2 amps. So how do we work out resistance? We again go back to resistance is volts upon amps, 11 upon 2, so it's going to be 5.5. So we can, again, by mental arithmetic, work out that that resistor is going to be 5.5 ohms. Let's just have a look at the memo. Again, they start with Ohm's law, resistance is volts upon amps. You've worked out that the external potential difference is 11 volts over 2 amps gives us 5.5 ohms. And frankly, again, you just need one option and you just cross out all the other options because you only want to learn one option, right? You don't want to learn lots of stuff. You just need one option. The same thing, we don't need these options. We've already got our answer there. Let's go back. So far this has not been hard. Switch S is now closed. How does this change or affect the reading on the voltmeter? Choose from increase, decrease, or remain the same. Explain the answer. Okay, let's first get the answer. So that's for 4 marks. So do you remember that experiment we just did a few seconds ago? When there is no current flowing, the voltage is at its maximum. It's 12 volts. But the moment a current flows, we lose some voltage here. So and then we said if we short it out, if that resistance is nothing, if we just have a short circuit, this voltage drops completely. So it's telling us that when this current, when we short this out, there's no resistance, we get a high current, we get a low external potential difference. So the moment we just short this out or reduce the resistance, this voltage that we'll see on this voltmeter will drop. So now look at this here. We have a switch. At the moment we have no current through here, but the moment we close the switch, we've now got 2 channels for current to flow. We've got this channel and we've got this channel. Before we only had the bottom channel. So now we've got 2 places where current can flow. So when you have resistors in parallel, they actually reduce the resistance because here the current can flow through there, and the current can flow through there. So if now got an option of going through the 2 or the 5. Remember this, we worked out 5.5. That's 2. Hey, it's going to easily be able to get more current going through the 2. And so we're going to get a much bigger current. Much bigger current means a lower voltage. So our external potential difference, this voltmeter will read a much lower voltage. So it will decrease. How does this change when we close the switch? It will decrease it. Explain the answer. Well, we've already explained it, but let's see how they explain it. So let's go to their memorandum. And they say it decreases. There's your mark. Total resistance decreases. That's what we said. Current increases. Here they say lost volts increases. Remember when we shorted it out, we lost 12 volts. So the lost volts is whatever we have is the difference between 12, the EMF, and whatever the voltmeter will read. So we've said the lost volts, the volts that get lost, will increase, and therefore the external potential difference will decrease. So I would recommend that you actually just learn that. It is so useful for you to learn these things. Now, if I was a parent, so that's the end of that question, I would say to my child, I adore you, but I'm off to work now, you're on holiday, I want you to learn 4 of these past exam questions, their answers for today. Don't give me that look. I want you to pull your thumb out of your bum, get your mind out of neutral, and learn, memorize 4 memos of 4 questions for today. And when I come home, I'm going to test you. And if you don't get it right, I'm going to take away your cell phone, your computer, your pocket money, and ground you for the week. So I would force, what are you sitting here? For 12 years I've subsidized you at school. Now you must pull thumb out and you must go ahead and pass your matric exam. I wouldn't put up with people just lazing about and, hey, you must pass your matric exam. So I would give them a little pep talk like that. So, but that's just me. I'm sure that you would be able to phrase it much better. So there we've shown you how to solve this question 8, where we encountered EMF and internal resistance of a battery. But look, in question 9, which we're going to do next, we again encounter EMF and internal resistance. So they really went to town last year in 2018. And if this question was really very easy, in the old days we'd call it a B stream or C stream question, or in slightly more modern times a higher or standard grade. This would be a standard grade question. And in the future they're going to call it a science lit. They're going to have to invent, just like they did maths lit, they're going to have to invent physics lit. For this would be a physics lit question. But the next question, question 9 on circuits, is going to be a physics tough question. And so we'll do that question next. But it's going to help if you remember what EMF and internal resistance are.